I'll be presenting our research titled Separated Intra-Modal Fusion Prompts for Compositional Zero-Shot Learning. And so the main area of our study is the CZSL, which is the Compositional Zero-Shot Learning. So it focuses on recognizing subtle differences in meaning and effectively combining states and objects by leveraging both known and unknown concepts during training. And this area of research is critical because it allows models to generalize and adapt to unseen combinations of states, and also enabling them to handle dynamic and evolving scenarios without constant retraining. So existing methods have primarily concentrated on either configuring prompts or using prompts to fine-tune pre-trained vision language models. While these approaches have made progress, they still struggle with accurately identifying subtle semantic differences and effectively composing states with objects. This limitations becomes particularly evident in complex scenes involving multiple objects and intricate relationships. To address these challenges and construct a more efficient and effective CZSL technique, we proposed a novel method that enhances attribute recognition performance. And our approach used diverse prompt learning strategies combined with an and intra-modality fusion synthesizer. And this fusion synthesizer is designed to improve scene understanding by capturing subtle semantic distinctions and effectively processing multi-object environments. So, for example, when encountering a new thing, such as a blue cat, people often attempt to name it despite the challenge of linking blue and cat together. CZSL aims to recognize and distinguish new concepts, and also a detailed textual analysis is needed to understand the semantic differences. Then it leverages visual information for matching. So previous researches in CZSL task have focused on connecting states with object information to improve prediction accuracy for the final pair. And after emerging clip, researchers use a compatible encoder and prompt, leading to better performance. And those previous studies use soft prompts for pair labels, which is compared to hard prompts. So instead of using just pair prompts, we suggest separating them into state, object, and pair prompts. And the features are updated through the suggested modal fusion synthesizer block to better understand complex intrinsic relationships in the scene. So the decomposed text and image features based on separated prompts can be helpful rich information to understand complex scenes. And we introduced the and intra-modal fusion with decomposed prompts to improve CZSL with prompt learning techniques. And the first related work is CZSL, and its purposes can be described as written on the right side. It usually aims to improve the attribute recognition and effective scene understanding, handling subtle semantic differences, and also can combine multiple object scenes. And it often uses the diverse learning. And its challenges can be noted as the complexity in implementation, requiring extensive training data, potential for overfitting, high computational cost, and limited generalization ability. And one of the recent paper is DFSP, and it applied a pairing prompt that combined with soft and hard prompt, which is composed of learnable tokens and a photo of state object. But it struggles to capture subtle language differences using fixed prompts for pairs. and therefore we develop a method for a better understanding of the connection and semantic differences of vision and language using hard and soft prompts. We conjecture those techniques are too simple to capture all the complexities in visuals and text, and also aim to develop a better method to understand the connection between vision and language, particularly in the CZSL task. We propose a learning method that applies hard and soft prompts to understand semantic differences. And the second related work is prompt-based learning. So the prompt has been utilized as a tool for fine-tuning in NLP, natural language processing, and multiple prompt-based learning researches are done. For example, visual prompt suggested the way to use the prompt in the computer vision field. And a red circle has shown a remarkable visual prompt in fine-tuning with only the insertion of the red circle. Those modify prompts for the model instead of adjusting the entire architecture, which is more efficient. And also in CLIP, fine-tuning task, previous work suggested the prompts to guide the model toward image classification goals. Prompt tuning can quickly adjust pre-trained models to diverse tasks without extra training. However, the research concerning the identification of an optimal prompt for CZSL is currently lacking, and also it indicates the importance of this study. So before getting into the method, some formulas must be described. The state set, it can be noted as A equals to the set from S0 to Sn. And for the object set, it can be denoted as large O is the set of O0 to OM. And the composition set indicates the C equal to the A multiply O with size N by M. And subsets of the composition set can be described as C, but C as for state and CO for object do not have same part of data since state label and object labels are not the same. And the training set T can be described as input image X and scene composition label set CS. Since unseen data is not provided in training, it only provided in the test so we can check how the model can recognize the unseen data in testing. So the shown image demonstrates the overall structure of how MFSB block works. And the description of MFSB includes both intermodality fusion and intra-modality fusion, and those distinguish text prompts for each element. So the visual features are represented in a circular form, while textual features are depicted in a diamond form. Using interfusion modality indicates that the textual content can strengthen awareness of each visual feature, especially for object and state. And through the intrafusion modality, the output of the interfusion modality is can exchange the same type of feature content, but has a common point. So in visual, a different object, but the same state is inserted as key and value. And in textual, the object that is most relevant to state labels is inserted as key and value. And the order of the fusion process is that inter first and then interfusion modality. So the first input text prompt is a hard pair prompt. It is denoted as a p-hard pair, and it is composed with state and object texture features, which goes through the image encoder EV, text encoder ET, and norm calculation. And then we compute the similarity score for the pair classes, which is based on the cosine similarity between vision and language vectors. Then it computes the cross entropy loss with ground truth pair, which is denoted as L hard pair. The other input text prompt is soft state and object prompt. it applied to capture diverse attribute and object features, and it overcomes the pair prompts limitation that is not enough for detailed content in complex scenes. And it also enhances the understanding of individual elements and their relationships. And the other input text prompt is the self-separated prompt, which is composed of learnable vectors and labels, and it can be denoted as psoft attr and psoft obj. It contains prefix context, which is learnable vectors with state and object textual features, and the matching scores are computed for each of them. And also the loss are computed for two cases written as L soft attr and L soft obj. And for MFSB block, it takes the input from previous pages, visual and textual content. And MFSB improves state and object features by combining and breaking down text and images through two types of fusion. So first, it combines vision and text features through Intra-Modality Fusion, and then it goes to the Intra-Fusion modality, which works only with the same type of features. So I'm gonna show table 5 later, but the best choice was using Intra first, drive the best performance compared to other choices. And this part guides the object, state, and pairing information in Fusion and the composition stages that improves understanding of information processing over time. In intra-fusion stage, cross-attention mechanism is applied for fusion part. So for pair visual and textual features, its key and value are set as vice versa pair features. And for state and object, its key and value are set as vice versa VL features, but do not exchange between state and object. So for ATTR, which indicates state, it only do cross attention with ATTR visual or texture features. And for OBJ, it only undergo cross attention with OBJ visual or texture features. And after that, each pair, state, and object matching score are computed between vision and textual features. Then its loss are computed with ground truths for three types. And those can be denoted as L inter pair, L inter ATTR, and L inter OBJ. And in intra-fusion stage, it also contains cross-attention mechanism, but only for ATTR and OBJ features, since it contains specific intrinsic contents. And for the first case, the query is state, visual, or texture, and key and value might be feature from OBJ. So that's the difference from the interfusion stage. And this part helps that state can contain object information, but remain the state content as the main. And for the second case, the query is object, visual, or texture feature, but key and value are state features. Through this case, each intra-ATTR and intra-OBJ matching score and losses are computed, and loss can be written as L intra ATTR and L intra OBJ. So in summary, the shown figure is the matching loss to understand how it matches through the MFSB block. And the total loss from the beginning to the end can be denoted as the formula below. And in this case, the alpha, beta, gamma values are set as 0.2 in the experiment. So in experiment, we conducted with 3 challenging data sets, MIT State, UT Zappos, and CGQA are are popular datasets for CZSL tasks, which contain state, object, and pair image and labels. And experiment scenarios are two types, closed and open world, which has the difference whether it contains every possible unseen cases or only contains controlled environment. And the metrics are HM and AUC, and those are total accuracy and the balance between true positive and false positive. And in every experiment, PyTorch 1.12.1 and Atom Optimizer are used, and the model is trained for 20 epochs with Clip VIT large 14 model. And the hardware we used is one NVIDIA RTX 4090 GPU. So these two large tables are the main results for open and closed word settings. And the results demonstrate that the method was effective for CZSL unseen, seen, HM, and AUC cases by improving the accuracy. So we compared our method with previous CZSL models, which includes DFSP, AOP, LE+, TMN, SIMNet, COMPCOS, CGE, co-CGE, SCNN, KGSP, and CSP. And those are all from the major AI conferences. And we investigate various fusion methods, including separated prompts and MFSP, and which includes the two types of fusion modality. And the table 1 and 2 show that our method outperformed on 3 data sets compared to other models. And we improved AUC scores of 5.4% on MIT States and 36% on UT Zappos and 10.5% on CGQA, and surpassing by 4.3% overall. And also there's a 6.8 increase in HM on MIT State's data set compared to other methods. And also it shows a higher accuracy on both seen and unseen data sets in this experiment. So based on the results, the two types of inter and intra fusion with decomposed prompts are the most effective for prompt composition in both open and closed word settings. We improve the image and text features through different fusion types, which focused on state or object recognition can yield better results than a basic fusion approach in the language branch. And we also conducted 3 types of evaluation studies to demonstrate the effectiveness of proposed methods and identify the best prompt format for CZSL. So table 3 identifies the best prompt combination, and table 4 compares the components of the prompt, and table 5 demonstrates the comparison of fusion techniques. And every experiment is conducted with the MIT State's dataset in the open world setting. On analysis comparing hard and soft prompts is presented in table 3. So previous research often used a mix of hard and soft prompts or just soft or hard prompts for training. However, using hard for pair and soft for an object state showed the best performance overall, and the hard pair refines information from the inputs to enhance comprehension of the scene. Table 3 illustrates the importance of appropriately using both hard and soft characteristics based on the label to understand complex scenes. And table 4 indicates a higher accuracy with 3 types of prompts compared to a single pair prompt. So previous studies have used only just single pair prompt. And our research found that the best approach uses 3 types of separate prompt components, which separate object and state within the pair prompt. Using a specific state and object prompt demonstrated the effectiveness in enhancing the comprehension of each element's visual and linguistic content, resulting in increased performance over time. And also, the deconstructed prompts helped clarify intricate relationships. And the table 5 displays results of no single and both, but different order of fusions. The results show that MFSB is effective with improved accuracy metrics, and some parameters from separated prompts pass through the MFSB block to access important information for understanding complex scenes. And interfuse features make successfully each vision and language content on each perspective, and intrafused features updated content that has relevant vice versa elements. Also, the order after intrafusion for interfusion was the most effective to make a response to new on-scene compositions. And this is the sample inference, and we can compare between baseline and hours. And as shown, hours can predict accurately by a better understanding in intrinsic relationships. And the consumed time for inference was 41 milliseconds. I think it can also be an application for the real world usage. And in conclusion, our study introduced the MFSB with decomposed prompt, a novel method designed to address the challenges of nuanced state-object composition. By combining hard and soft prompts, we captured both detailed multi-object information and fine-grained features in complex scenes. The integration of inter and intra-modal fusion, it enhanced the understanding of visual and language context, making the model more robust in multimodal learning tasks. Importantly, we demonstrated the value of dividing prompts based on their purpose, improving training efficiency, and achieving better comprehension of diverse data. Through extensive testing on 3 challenging datasets, our approach consistently outperformed existing methods, showcasing its potential to drive advancement in multimodal learning and training optimization. Moving forward, this method provides a strong foundation for exploring even more complex and dynamic training scenarios. So this is the end of the presentation, and any question?